Hello, in this video we're going to look at find the volume of a solid generated by revolving a curve around an axis of rotation. Except this time we're going to look at something called the shell method. Okay, so we looked at disk method and washer method, and then shell method is a third way to find these volumes by revolution. In this specific problem, we asked to find the volume of the solid generated by revolving the region bounded by y equals 4x minus x squared and y equals x squared about the y-axis. So we're revolving around the y-axis right here. I already did some of the legwork by putting in a graph of those two curves. The green one here being, of course, the upside down parabola, 4x minus x squared, and the red being y equals x squared. So that's some of the legwork where you'd have to graph it, and you have to find kind of where this region intersects. And it looks like we're revolving the region bounded by those curves. So this area right here gets thrown around the y-axis, and it's going to pop up on this side. And we want to find the volume of that surface when this thing would be rotated around, creating a kind of U-shaped cup of sorts. Okay, so it'd be revolving around like that. Now, the disk method is the one kind of often first talked about, and that's the easier one. But what happens in this case when we use the disk method? Well, our representative slab, or our little portion of it, would have to be like this, and it would revolve around until we get here. So that would be one of our disks. It would turn out to be a washer because we got this hole in the middle. But what do you know with this? In this case, our disks are filling up on the y-axis, okay? You kind of stack your disks up here to find your volume. Well, if I'm filling up on the y-axis, my integral is going from 0 to 4. That means I'm integrating with respect to y. That means this function, 4x minus x squared and y equals x squared, are going to need to be in terms of y. It has to be x equals something in terms of y. That's a problem. I can do that all right for y equals x squared. That's just x equals the square root of y. But how am I going to do that for this? I can't really solve that function, 4x minus x squared, for y. Okay, I'm going to run into issues with that. So thankfully we have this thing called the shell method. It's called the shell method because you take a bunch of cylindrical shells and you stack them together. Kind of like Russian nesting dolls, I like to think of it. In this case, I look at my slab being vertical. In fact, it is parallel to our axis of rotation. And I'm going to rotate that around. And notice, if you can imagine this thing right here, rotating around your axis of rotation, it will create that cylinder. It does. It creates a cylinder. Now I need to find the volume of each of those cylinders, because then I go and I would have another cylinder outside it. And then I would go yet again and I would stack another cylinder. And you see, you find the volume of all these individual cylinders, and you keep going out until you would fill up all your region with these cylinders that nest inside of each other. They're a bunch of shells. Again, I like to think of those Russian nesting dolls where you open up the biggest doll and there's a smaller doll inside. You open up that one, there's a smaller doll inside of that. And if you find the volume of each one of those shells, add them all together, you would find the volume of our region, volume of our solid generated by revolving that region. How do I find the volume of one of these cylinders? So bear with me in this explanation. It's kind of neat. Volume of a cylinder, well, the volume of this shell cylinder, we can think of it as finding the lateral surface area of that cylinder, lateral surface area being just the surface area of the area between the bases. So everything except the bases. That area is equal to 2 times pi times r times h. 2 times pi times r, which would be the circumference times h, which is the height. That gives you that area of the folded up rectangle between the bases. Okay, but that's surface area. That's not volume. But what if we give it a third dimension? We give it some volume. Like, what is the thickness of that little slab that we rotate around? That's the thing that gives the volume. That gives the volume of that shell. Well, that thickness is going to be dx in this case. Okay, because it's how wide it is here. And for our calculus terms, that width, since I'm moving along the x-axis, is going to be dx. Okay, an infinitely small thickness. And that way we can think about it, that surface area with just a little bit of thickness. Now it blooms into a volume of a really thin cylindrical shell. Okay, so now looking more specific at it, my volume of one of those shells is 2 pi times r times height. What is the radius of that? The radius is going to be a function. It's going to be something that changes because the radius of this blue shell is one number, but then the radius of maybe this orange shell is different. It got bigger. Okay, this new radius is a little bit bigger. When I revolve about an axis, it's sort of easy because my radius here is going from x equals 0 to x equals 1 in this case. So my radius is just 1. Let's say I get a shell way out here. Now what is the radius of this shell? It is 1.5. And notice how 1.5 is my x value here. So my radius is just whatever the x value is. Okay, I move out here. The radius of that shell would be 1.75. Your radius in these shell problems is always just going to be x or y if we're rotating about the x-axis, or it might be your x minus your axis of revolution. So when your axis of revolution changes from just being a y-axis or x-axis to maybe x equals 4, it will change a little bit. But your radius is always going to be that variable which you are integrating with respect to. Then there might be a plus or minus of that axis about which you're revolving around. In this case, we're revolving around the y-axis, so it's easy. Our radius is just x. Okay, let's clean this up a little bit. Go back to our blue cylinder. Height. What would be the height of our cylinder? This is the one a little bit easier to see. The height is between these two curves. As soon as I move my shell back here again, my height is, again, just bouncing between those two curves. So the height we are seeing is also a function. But this function, it's the difference between your two curves. And just like find the area between curves, it is top minus bottom, or it might be right minus left if you're revolving around a horizontal line. So in this case, it's going to be the top curve of 4x minus x squared minus the bottom curve of x squared. Okay, and that would be the volume of one of the shells, but what we said, we want a whole bunch of shells, an infinite number of shells, and to find the volume of each one, and then add them all together. And guess what? That is an integral. So using this shell method, the volume of a solid by revolution is equal to 2 pi times the integral from a to b of the radius times the height times dx, in this case, sometimes it's dy, remembering that this r is going to be a function. This h, your height, is going to be a function. Okay, you can pull out the 2 pi because that's just a constant there, 2 times pi. And the integral a to b, those would be the two bounds of your region. So in this case, we're going to go from 0 to 2. Okay, now let's set up the integral specifically for our problem. So volume is equal to 2 pi times the integral. I'm going from integrating on the x, so my shells are filling up on the x, so I'm going from 0 to 2. I can see that on the graph. If you needed to find those bounds, you would just set the two functions equal to each other. 4x minus x squared equals x squared, and then solve for x. But we can see on the graph it goes from 0 to 2. Now I think about my radius. The radius of this is just whatever the x is, so as x changes. So that is my radius. The height of each shell, it bounces between the two parabolas, so you go top minus bottom. So it's 4x minus x squared minus the other function x squared. That's the height. And then the thickness of each of those shells, to give it an actual volume, is dx. Okay, now we can simplify this a little bit. Before we integrate, I will first combine on the inside, and you get 4x minus 2x squared dx. Let's go through it one more time and distribute the x. 4x squared minus 2x cubed. We've done the heavy lifting now, and now it is just on to doing some power rule integrating. Okay, I moved our general formula out of the way. Power rule, so you add 1 to the exponent and then divide by that. So minus 2x to the 4th over 4, and we are going from 0 to 2. Let's write this one more time to simplify that second fraction. So that's x to the 4th over 2. Now evaluate at 2, and then evaluate at 0. So at 2, you get 4 times 8 over 3 minus 2 to the 4th, which is 16 over 2. And then minus, evaluate at 0, in this case is just 0. So now I have 2 pi times 32 over 3, and then 16 over 2 is 8, which is the same as 24 over 3. So I get 2 pi times 8 over 3, and that gives us a volume of 16 pi over 3 units cubed. And we found that volume using the shell method. One last thing to comment on. Notice with the shell method, my slab, my representative slab here, is parallel with my axis of rotation. Okay, I'm rotating about this y-axis. It's parallel to it. When your slab is parallel to the axis of rotation, you do the shell method. But if your slab has to be perpendicular to it, so there my axis of rotation, my slab is perpendicular, that would be a disc/washer method. Okay, I hope that served as a good introduction to the shell method. In the next video, I'll do it where we rotate this same region, except about the line x equals 4, which just adds a little bit to the radius. So you can check out that one for rotating about a non-axis.